Welcome to X-Ray Spatial for raster analysis. Uh, we have Brendan Collins with us, and one of the sweetest people I've met, must say. So let's get started, Brendan.
Thanks, and thanks, Scott, for the great ML presentation. Is everyone able to see my screen okay? Is the screen share coming through?
Yes, Brendan, we can see you.
Great, thanks. And I'm sorry for the bait and switch on fine-tuning raster analysis, but really this presentation is looking at X-Ray Spatial, the project, and introducing some of the features. My name is Brendan Collins. I'm the co-founder and principal at MakePath, which is a spatial data science company based in Austin, Texas. We use Dask and a lot of the tools within PyData, and so we're really excited to present here at the Dask Summit. Today I'm going to be presenting on an open source project that we maintain and contribute to very actively, which is called X-Ray Spatial, which provides common raster functionality on top of X-Ray data sets. And by raster, I'm speaking a little bit from a GIS analyst mindset, where we consider rasters to be, like most folks, regularly gridded data sets. And in the GIS world, we always have this choice between using vector data sets or raster data sets. All the tools that we're going to be looking at today are going to be for rasters or large images. So some of the groups of tools that are available within X-Ray Spatial include surface analysis tools like slope and curvature, hill shading, proximity tools like being able to generate distance grids, zonal tools, which help us calculate stats within areas of an image, focal tools for passing kernels across an image, finding hotspots, 1D classification, multi-spectral tools, and pathfinding tools. And we're going to look at each one of these categories briefly and then see some examples of using this library with Dask. So in looking at surface tools, many times we have collisions in names. So within the GIS world, we call the first derivative of elevation slope. If you look at NumPy, you may see words like gradient. Now, this library X-Ray Spatial is meant to speak to geography professionals. And a lot of the names that you'll see here are ones that are common within this domain of spatial data analytics and GIS. And part of the goal of this library is to bring disciplines together. In working with Dask and working with a lot of the tools within PyData, there's a lot of overlap in use case, but the names of the tools can be difficult for GIS professionals that are not accustomed to this ecosystem. So X-Ray Spatial aims to bridge that gap by using great technologies like Numba and Dask with tools named for GIS analysts. As I mentioned, we support proximity tools. There's 3 general types of proximity tools that we're interested in. One is just generating distance grids, where we may have a raster here that has in this case, it's a line that has been rasterized using Datashader, but we want to generate a distance grid to this line. In this case, the distance grid was thresholded, but that's the first type of proximity tool that we look at is distance grids. We also do direction to the nearest feature, and also generating grids that show allocation or which feature are you closest to based on its ID. We're going to see a little bit more of that in the proximity notebook. Zonal tools are incredibly useful. Zonal tools would allow you to take one image that represents zones as categories to help summarize a value image. So in this case, we can think of something like if we had elevation and we had a bunch of land parcels and we wanted to calculate summary statistics for each land parcel based on the elevation, we would use a zonal tool. Focal tools look at the area around pixels. Smoothing filters are a common focal tool. Within X-Ray Spatial, we provide a general purpose API for writing focal kernels. So this includes doing a focal apply operation where you can create a kernel as a NumPy array and then pass it over the image in a convolution There's also a hotspots tool in here. We're not going to be looking at that today, but if folks are interested in hotspot analysis, which would look at the area around a pixel and compare those stats to the global stats to find cool and hot areas within your image that are statistically significant, check out the hotspot tool. Classification tools here are named for GIS professionals. These are very classic 1D classification binning tools, things like binning by quantiles and equal interval, doing natural breaks or jinx, which is basically 1D k-means, and then also just generally reclassifying the pixels in an image to different bounds. Multi-spectral tools allow us to do classic band math on satellite imagery. So if we're taking multi-band images from, say, Sentinel or Landsat or MODIS, we're able to use those bands and look at their signatures to pull out significant features. The classic one would be NDVI, which some folks may not know, but NDVI was actually developed by Kodak, the analog version of NDVI, for the D-Day invasion to pick out living from non-living surfaces to find concrete versus vegetation. So that's a lot of what these multispectral tools are doing, is taking satellite imagery and then being able to pull out relevant features or classify areas into living or non-living, or also the amount of vegetation in an area in the case of NDVI. Most of those are actually pretty simple algorithms, but they're semantically represented here. So we have a name NDVI. So when you look back at your code, you can see, okay, I was doing NDVI here because you called the X-Ray Spatial NDVI function. We have some very basic pathfinding, which would allow you to route across through an image using pixel connectivity. In this case, this is an image of I believe the Austin area, and we're routing through some road networks. This is not Daskified yet, but we're going to see which tools here work with Dask and which don't. So we have a goal of having all of our tools Dask enabled to run across Dask clusters. We're not fully there yet, but we do have a roadmap of where we're at that's continually updating. So just diving in from the slides, let's actually look at this library. So we're here on GitHub, and we can see X-Ray Spatial. You can install X-Ray Spatial using Conda Forge with Conda install Conda Forge X-Ray Spatial. And you can also here use our CLI to get example data. So you can run our full user guide, which includes various notebooks that address these different topic areas. So here in our feature list, we have the module, the specific tool, and which array backends to X-Array are supported for that tool. We're trying to target 4 different use cases. One is the just classic NumPy on your local machine use case. That's the first one we always implement. Second is having a Dask array backed X-Array data array, which would allow us to compute over a cluster or over multi-core scenarios. Then also supporting CuPy for CUDA-enabled GPUs. And finally, the Dask GPU cluster, which would be a cluster of CUDA-enabled GPUs. These are the classic 1D binning methods here. But then as we go down the list, we'll see the other categories and where we have support and where we lack support with these green checks. So we see in focal and multispectral. I'm just going down the list here. Pathfinding is a little sparse for Dask support right now. We're also working on proximity very actively to support distributed proximity. And then we have surface analysis tools and zonal tools. So we continue to build this out. And over the next 6 months, we hope to have this all filled out and have a 1.0 release. Here we can see an image that was generated using data shader and X-Ray Spatial of Crater Lake National Park. And some of the layers that were composited here include roads, we have elevation, we have a lake feature with some proximity gradient, which might be hard to make out. But this is a look at a little bit of how we can build up a output image and do some cartography using X-Ray Spatial and data shader. X-Ray Spatial has a bunch of dependencies that are within the PyData ecosystem, and those include data shader as the rasterization pipeline. So when we want to bring in vector data into a common raster space, we can use data shader to do that, which can easily rasterize points, lines, and polygons, tri-meshes, quad meshes, and resample other rasters to a similar, to co-register images together before doing analysis. And let me just say that none of what we're doing in X-Ray Spatial would be possible without the work of folks at Anaconda and Quantile and Coiled, certainly, as we're going to look at some examples of deploying X-Ray Spatial on Coiled, and the larger community. So a big shout out to all those folks. There's some optional dependencies here, including Rasterio, which wraps Gdal. There is an effort here within X-Ray Spatial to provide Gdal-free spatial analysis tools. That would mean that you're able to extend these tools without having to drop down to the C or C++ level and stay within Python. We're going to look at the end at an example of how you can get involved in extending these. But let's dive into some of the user guide. So here I'm loading up, I have a Jupyter notebook, and I've loaded up the X-Ray Spatial user guide, which is available on GitHub in the examples area. And you see an example notebook for some of the different X-Ray Spatial modules. Looking at the surface analysis notebook, we're going to first start by generating some terrain data. And X-Ray Spatial provides a helper function called generate terrain, which will help you do this for a single machine. We're going to see an implementation of this across a Dask cluster in just a sec, though. So here I'm using some Perlin noise to generate some mock elevation data. That elevation data will help in running the tools. So here I'm using a elevation color map to add some realistic values for imagining our terrain. And we can see our first surface analysis tool of using a hill shade. So this is illuminating the terrain using a light source at a specific altitude and azimuth. There's this gives us another layer. This is an X-array data array object, which I'm then passing to data shader's shade function and applying a color map. And we can see the shadows now come out for our mythical terrain. We can use this along with our original terrain image to composite a color mapped version with our shade. And so this is using data shader stack to actually composite things. So there's a heavy integration between X-Ray Spatial and data shader, as X-Ray Spatial actually fell out of data shader. So I've been a core contributor on data shader and kept wanting to add more spatial functionality, which got a little overwhelming at some point. So it split out into a separate library, which is where X-Ray Spatial originally came from. So using a slope, which would be looking at the gradient of the surface, we can imagine identifying risky avalanche areas here using thresholding, and then highlighting those in red. So this would be kind of a common, might be a common analysis task using X-Ray Spatial, linked back to our mythical terrain here. Curvature is the second derivative of slope. I'm not going to look too much into that, but know that we have some curvature tools. Aspect is the direction of the slope, which what direction is the slope facing? You can imagine for avalanches that'd be particularly important, or agriculture. Viewshed is about doing line of sight. In this case, we have an observer and we have a mock hill here, and we want to see which pixels the user can see and at what direction they'd have to look to see them, and which pixels they cannot see. So we've run the viewshed tool, and now the pixels that we can see are highlighted. And this viewshed can be important for, say, seeing what coverage a line of sight cell phone tower would have. So we can have multiple observer points, and we can see the coverage of these points in line of sight to elevation features. So this is the surface notebook, which is the first notebook in the I know that will come off at some point. The first notebook in the user guide. in looking at proximity tools, I had briefly mentioned that there was 3 different proximity tools to consider. Distance grids, starting from a set of points, we can see that our first distance grid would generate an X-ray data array where each value is the distance to the nearest point. Also, doing proximity direction. So I want to just skip down to this, and there's a bit from the fire hose here, but we have proximity direction and proximity allocation. So here in proximity allocation, we have our same points, but we want the output raster to contain the ID of the closest point. So that's what proximity allocation is doing here. And we're stacking 2 images here to show the points and then their allocations. And then also proximity direction. So this is the direction to the nearest point. You can imagine how useful these could be for feature engineering for your models, where you're trying to find new features. Maybe spatial features could be helpful in knowing what's the nearest, say, point of interest, or what is the slope at that location, or passing over a focal kernel to understand stats about the area as they compare to the global image. So there's a machine learning use case here for X-Ray Spatial where you use these tools to derive new features for your models. Jumping over to some else, there's more notebooks within the user guide here. Zonal is certainly one of the very useful ones, and we're going to be focusing on Daskifying that very, very shortly. But let's look over at some tools that are already Daskified. So I'm moving over now to the Microsoft Planetary Computer. We're working alongside Microsoft to build more features for X-Ray Spatial and also enable it for Microsoft users that are using the Planetary Computer. In this example, we're using X-Ray Spatial's Multi-Spectral Tools to do a cloudless image based on several sentinel scenes. This is using Stack and PyStack. For folks that aren't familiar with Stack, Stack is a raster catalog, which would allow you to have a data structure that describes many different scenes of a very large raster. So we can think of Sentinel or Landsat and all the different scenes and be able to address all those scenes with a single data structure. And that's what PyStack enables us to do. In this case, I'm creating a Dask cluster. I'm using Stack to query data based on a bounding box and a time window, and a date time window. This is all running on the Microsoft Planetary Computer. We're sub-selecting based on some cloud cover, creating a Dask array here. And then we're able to do a median composite and then apply X-Ray Spatial's true color function to derive a cloudless scene. So this cloudless scene is something that that we're working on. I think just looking at it, we could probably use a little bit more contrast enhancement, but true color is one of the tools within the X-Ray Spatial multi-spectral module, along with NDVI and SAVI and a bunch of other band math. Another area I wanted to show was using X-Ray Spatial on coiled. So in a lot of our work, especially with GIS folks, we're not DevOps experts, and being able to have coiled to easily deploy a Dask cluster is really great. So in this case, what's going on here is that I've imported coiled and I've created an environment for X-Ray Spatial here called Surface Tools environment. I've specified a couple of dependencies, including X-Ray Spatial and noise. I'm then starting up a Dask cluster, and we can see the diagnostics dashboard that goes along with this Dask cluster on the right-hand side, connecting to that cluster, and then starting to do my work. So the first thing that I did here is just wrote a simple Perlin noise function to populate a Dask array with Perlin noise. So this is going to be our mythical terrain within Dask land. The other one was just on my local machine using NumPy. So what I've done is I've generated terrain, and then I've used client.persist to persist that data on the cluster. And we can see a couple of things. It's not a large array. It's only 16 gigs, but we have 256 tasks, and each chunk is about 64 megs. So now I have my terrain data, and what I want to do is actually run Hillshade on this. So I'm going to run, so I think I may have in presenting other info, may have brought this cluster down. Let me just get this back up, but let's see. I might do that on my time, but let's look at some of what we can do here. So what we did was we created a large Dask array of Perlin noise. We're then able to color map elevation on top of it and also run Hillshade. I would love to connect to this. Let's see if we can connect the client back here.
Brendan, we also have a few questions. If you
Oh, great.
like to answer
Great. Thank
those
you.
in the meantime.
Let me just look back at these questions here.
Would you like me to read them out?
That would be great. Thank you. I've lost that screen.
Yeah, okay, no worries. First question is, does X-Ray Spatial support any geometric median calculations?
Not specifically, but I'd love to talk more about that and understand exactly what that is. And we're always looking for new features, and so would really like to learn about the use cases for that and potentially add that to our roadmap.
Okay. Next question. How does the library deal with the NAN values? Does it rely on the XR function?
So we're using X-Ray as the main data structure, and so we don't mean to handle anything for you that X-Ray or NumPy wouldn't. So you should still be using all of the common, dealing with NANs from X-Ray or NumPy, but these are extra tools on top of that. And so the deal with setting no data is still an issue here.
Awesome. Alexander asks how to load a Geotiff into X-Ray Spatial without Gdal. And there's a follow-up question to that. How to load a Geotiff? Oh, it's the same. All right. Sorry. Yeah.
Yeah. So X-Ray Spatial does not handle any I/O. So we delegate loading Geotiffs to basically to Gdal. So it kind of begs the question there, but so there isn't specific I/O here. It's only analysis functions on top of arrays that you have in memory or you have as Dask arrays. We'll do a smaller array here. Let's do a slightly smaller array just to get through something. So we're now connected into a coiled cluster. We're persisting some terrain data, and then we're going to run this hillshade and persist the hillshade, and then see if we can generate this image, and then classify the terrain into 5 categories. This is mostly just to also show the Dask integration and see that's running live. The ease of spinning up coiled clusters makes it so using Dask and using distributed computing is actually an option for us, because we really don't want to get involved in manually setting up clusters, and we want to focus on our spatial data science problems. So here we're loading up a bunch of data. We're running the hillshade operation now. And then we're going to subselect and shade and then stack and look at our output. And so this is just a subselection of our data, but we generated a bunch of Perlin noise and then are compositing together the hillshade and the terrain. And we can see some of our tasks finishing up as we go. And then let's do just a simple quantile binning. So we're going to import from X-Ray Spatial the quantile function. We're going to bin the elevation into 5 categories. And we can see this kick off across all of the different blocks in the Dask array. And then we're outputting, we're going to just shade those categories into different groups. So this is just a nominal analysis that was meant to show the integration with Coiled and how easy it is to spin up a cluster and then load up X-Ray Spatial and get some data going and run that. That was a great question about the Geotiff, and that Geotiff is really where, when we look at the dependencies for X-Ray Spatial here, which is why we have these Rasterio and Gdal optional dependencies here listed, is because X-Array and what I would use would be Rio X-Array. So Rio X-Array has some nice read methods for also assigning and managing the coordinates on top of the X-Array data array. So I tend to, if I'm going through Rasterio through Gdal, and we should update this, I would be using Rio X-Array. We're currently also working on reprojection and resampling methods. Right now, our reprojection is just going to be wrapping Rio X-Array to project each block and then stitch them together for Dask arrays. So that's coming soon, and we're also working on a zonal tool Dask module so that we can run all the zonal tools across a cluster. You'll also see here Geopandas. So Geopandas being the best library for loading up vector data, and then we can convert that to a spatial pandas geodata frame for rasterizing it with data shader, or use this, in other ways. So all of these dependencies here are optional. The yellow dependencies are optional, and we're also building out the CuPy support. So CuPy support is available for the multi-spectral module and some of the surface tools, but in general needs better support. So when we have everything Daskified and CuPyified, then we'll have our 1.0 release. But we usually release on a weekly schedule here. So we're right at we're very close to 300 stars. I feed myself on GitHub stars, so I'd appreciate any love there. But just wanted to thank Coiled and thank Dask and Anaconda and Quantile and Peter Wang and Jim Bednar and all the folks that made this possible, that supported this and helped us along the way.
You should refresh the page, Brendan. We crossed 300 stars, I think.
Oh, that's exciting. That is exciting.
Awesome. So we have like 5 to 6 questions. They're on the Q&A box, and there is one question in the chat. So you can just go ahead and answer those. I'll leave you as you can stay a presenter and just let me know when you've answered, and I can.
Great.
I'll make an attendee.
Great, thank you. Yeah, just
thank you so much.
Thanks so much.